Okay, so let's continue going through dimensionless boundary layer conditions, or equations. But now what we're going to do is we're trying to use our dimensionless equations to come up with correlations. You know, aside from the fact that we went through and identified these dimensionless groups, the Reynolds number, the Peclet number, and the Eckert number in our last analysis, really the point of this is to get to these non-dimensional or normalized equations that we can use to develop correlations. So at this point now, we're going to go through and start doing a little bit more justification of what is it that we need to include in our correlation. So this is our summary of where we left last time. So if you remember, we have our original equations over here. These are our original governing equations, and we went through some simplifications and said, okay, this is our boundary layer simplification for continuity, right? And then here we had a simplification for the x component of momentum. Again, making this substitution here where we say our pressure is the free stream pressure as a function of position. So this is our simplified equation here. The y momentum went away entirely, saying basically dp dy is about equal to 0. And then here's our energy equation, and this simplifies to this. So we were able to get rid of change with temperature as a function of position x, the second derivative of that. In the viscous term, we were able to get rid of basically the whole viscous term, except for this part here, right? And so we see that showing up here in our equation. After normalizing it, then of course we have what's on the right-hand side as the final result there. Okay, so let's see. So what we're going to do now is we're going to go through our correlation, as I said. So the point here, the goal of this analysis is to figure out what in our what in our equations is sort of functionally dependent on what else in the equations. What I mean there is, can we go through and really boil things down to the very minimal set of things that we could express a correlation in terms of? Can we boil it down to just velocity, for example? Can we boil it down to just Reynolds number? What is it that we can express our correlation in terms of? And you know, having had heat transfer before, probably you kind of know where this is going to end up. That we are going to be able to get down to things like a correlation in terms of a Reynolds or Prandtl number. But it's useful to see how that happens. So let's kind of go through a couple of steps. So let's start first with the momentum part of things. So we're first going to look at these two equations up here. Right? The top two equations up there can be solved independently of the energy equation. Right? We can come up with a velocity boundary layer that doesn't involve the energy part at all. So we'll start with the momentum part first. So if we look at these equations, we have kind of two independent variables, right? We would maybe want to solve for a velocity profile in u and a velocity profile in v, and have two equations, one for u, one for v, and represent the velocity that way. So we would say our u tilde is equal to some function. We'll call it rated this way. So u tilde is a function of what? So if we look in the equation, what is u going to have to be a function of? We're keeping in mind that we're doing this for u and for v separately. So u is going to have to be a function of, well, what else appears in the equation? We see that there's an x in there, right? So it's going to be a function of x. It's going to be a function of y in those two equations. We see that there's this Reynolds number, right? So the Reynolds number, Re, is going to be in there. And we also have dp infinity dx. P infinity dx. Right? So we could write our u velocity in terms of a function that is dependent on these things. We see that, okay? For v, we can do the same thing. So v tilde is going to be some function of basically the same things, right? It's the equations are pretty symmetric in that way. So we have x, y, Reynolds, and dp dx. So those are both expressions that we could come up with. Okay, so how does this help us? Well, let's look at now what we're, if we're doing this for the momentum, what we're trying to do is get to some engineering quantity of interest that we care about. We don't really care about the velocity. We care about, for momentum, probably the shear stress or the friction coefficient or something like that. So let's do this for shear stress. Let's write the expression tau s is equal to, what's the definition? The definition of shear stress is going to be mu times the partial u with respect to y, evaluated at y equals 0. Shear stress is the velocity gradient in y at y equals 0, right at the surface. So if we go through and do our substitution for our non-dimensional variables on that, we end up with that's equal to mu times the partial of u tilde times u infinity over the partial of y tilde times L. All that at y equals 0. That's our non-dimensional variable definition of tau s. Okay, so go through, so we can pull out the constants there, and we end up with just tau s is equal to mu u infinity over L times the partial u infinity with respect to y, evaluated at y tilde equals 0. So actually y tilde up here too, right? So that's our shear stress for this. Okay, so we have this now. So we now want to go through and kind of represent this in terms of a friction coefficient. So what's our definition of friction coefficient? If we remember, it was just, we wrote it before as tau s is equal to friction coefficient times momentum. So if you solve for that, it's CF is 2 tau s over rho u infinity squared. Okay, so we now have our non-dimensional representation of tau s. So let's substitute that back in. So then we end up with CF is equal to 2 over rho u infinity squared times tau s, which was mu u infinity over L times the derivative du dy at y equals 0. Okay, what do we have? We have rho u L over mu appearing in that equation. So we end up with CF is equal to 2 over the Reynolds number times the partial du dy at y equals 0. Okay, so now we just went through this analysis. We kind of have used our normalized equations a little bit, and what we end up with is friction coefficient is dependent on 2 over Reynolds number du dy. So let's look back at what is u dependent on. So u is dependent on x, y, Reynolds, and the pressure. So actually the coefficient of friction, itself is going to be a function of the following. So coefficient of friction is a function of x tilde. Is it a function of y tilde? We're evaluating y, or we're evaluating the equation at y equals 0. So it's not going to be a function of y tilde, just because of our definition of coefficient of friction here. Okay, so it's not a function of y tilde. It is a function of Reynolds number, and it is a function of the pressure gradient, right? Because that appears in our u term there. So we end up with b infinity dx. Okay, so this is kind of a weird analysis we just did, but we went through and used our definitions and came up with this conclusion that just says our coefficient of friction depends on what? It depends only on position x. Right, so you have this flow over flat plate. Our coefficient of friction only depends on position x, not on position y. It depends on the Reynolds number, and it depends on this pressure gradient dp infinity dx, right? So great. So if we're going to come up with a correlation, then we don't need to have a correlation that's functionally dependent on y or v or any of this stuff. It only has to be functionally dependent on these things. So we can collapse things kind of down to these common sets of inputs. Okay, let's see. Yep, and so so this is our kind of conclusion from this. Any questions on that analysis? Okay, So moving on then to another kind of aspect of this. We just solved for, up here, we just solved for coefficient of friction, which is the local friction coefficient. This depends on X. That may be useful for some applications. Maybe you actually care about the total force on this plate. So in order to get to the total force, what would we do? We would take, here's our original stuff we had up here. We just decided this was true. In order to do the full force, we need the average friction coefficient, right? This guy here, which means we need the average tau. So to do that, we actually need to integrate over the entire length. It's fairly straightforward, but let's just go through it real quick. So we have tau s bar is going to be the length averaged integral from 0 to our length L of tau s times dx, right? That's just our definition of the average shear stress over that length. Okay, writing this specifically for this equation, it's going to be tau s bar is equal to mu u infinity over L integral from 0 to, now with our normalized variable, it's 1 du tilde dy tilde at y equals 0 times dx tilde. Okay, so that's our average shear stress for the normalized equation using the definition of shear stress. All right, continuing on, then we can write our coefficient of friction, C bar F, as then 2 over rho u infinity squared times mu u infinity over L times our integral 0 to 1 du tilde dy tilde at y equals 0, so y tilde equals 0 times dx. Okay, and then rewriting that, you can again see that there's the Reynolds number appearing in the first group of parameters multiplying. So then we end up with 2 over Reynolds times the integral from 0 to 1 u tilde dy tilde at y equals 0 dx. All right. So now what do we see in this integral? Right? We still have this Reynolds number appearing. We're integrating now across all of x. Right? This is dx up here. We're integrating across all x. That means there's not going to be any more functional dependence on x now. Right? And this is probably obvious, but we're taking the average, we're integrating over the full length, and we end up with now a correlation. We could write it out as follows. We could end up with a correlation. Let's see down here, C bar F is going to be C bar of F of Reynolds number and dp dx. Okay, so average coefficient, you can come up with correlations that are just based on the Reynolds number of the flow and the pressure gradient in the x direction. Right, so now that makes our job as people developing correlations even easier. Now we just have to think about those. And it's actually, I mean, I don't want to get lost in the fact that it's really kind of amazing that you can correlate or come up with a relationship for flow in this really complex situation in a boundary layer for really any geometry that's valid for this dpdx, and have a single set of curves that go with that. Right? It's kind of this really powerful conclusion. So I mentioned this dpdx is for a given geometry, or it is for a given geometry. What this means is that I'm solving this equation for the boundary layer. Right? The boundary layer is where this, where all the action is happening here. But the dpdx term is actually something that comes from the inviscid flow region outside the boundary layer. So what that's saying is, like, given a shape or given a geometry, given a type of problem, you can compute dpdx outside of the boundary layer and then give it to this correlation. So it essentially acts like a parameter, which means really our correlation only needs to be a function of the Reynolds number. That's kind of the conclusion here. Again, a pretty powerful thing. One other kind of side point here is sometimes, this is the coefficient of friction. So this is due to viscous effects. We also sometimes care about pressure effects due to flow over the body, which is through the drag coefficient. So just to give you the definition there, we have CD, the drag coefficient is equal to 2 times the drag force, FD, over rho U infinity squared, AP. All right, so just AP here is the projected area. Meaning that this is the area kind of exposed in the direction of flow. So if it's a cylinder, right, and it's flow kind of going over around the cylinder, the projected area would be the diameter times the length. Right. So that's our drag. And then just to note here, you can see that the coefficient of drag function is just a function of the Reynolds number. Questions on this? Okay. So let's look at just really quickly. Here's an example of how this looks. It's something you've probably seen before. So you have this chart showing flow over a sphere, and we're computing or correlating the drag coefficient as a function of Reynolds number. So this is actual experimental data. Right? The blue experimental data shows that as you increase in Reynolds number, your drag coefficient is going down. And the kind of powerful thing here is we have, again, for any geometry that's a sphere, right? Any geometry, any size, any fluid that's flowing over it, doesn't really matter. We can compute the Reynolds number, boil it down to this one curve, and then we can use this one curve for our correlation. Yeah, so it's kind of a cool result.